Okay, so in this video we're going to practice drawing some Lewis structures. So here the first molecule we're going to draw is ozone, O3. So our first step, we want to find out the total number of valence electrons. So we have oxygen has 6 valence electrons, and there are 3 oxygens in our molecule. So we have a total of 18 electrons for our structure. Now, because all of these atoms are the same, it doesn't matter which one of them I put in the center. I will have 3 oxygens lined up next to each other. I've used lines to connect them, and if you'll recall, the lines represent bonding pairs. So the next step, we want to subtract our bonding electrons from our total valence electrons. So here we've used 2, 4 bonding electrons. So we have 14 electrons left over. So I'm going to go ahead and put these all around the oxygens in lone pairs. So I have 2, 4, 6, 8, 10, 12, 14 electrons. So I've used the rest of my electrons and I'm good to go. Now you may be wondering, why did I put the electrons around these particular oxygens in this particular order? It really doesn't matter. If I had put them, maybe this pair over here, it would be the same. It would be the same thing. We'd do the same steps going forward, okay? So where you choose to put the lone pairs at the beginning doesn't matter, because the next step that we're going to do is we're going to evaluate the octet rule for each one of the oxygens. So when we evaluate the octet rule, we count how many electrons are around each of the atoms. So we have 2, 4, 6, 8 electrons around this oxygen, 2, 4, 6, 8 electrons around that oxygen, and 2, 4, 6 around this oxygen. So we see that this oxygen does not have its octet satisfied. So when we see that we don't have an octet satisfied, we want to share one of the lone pairs on the other atoms in a double bond to satisfy the octet on this central atom here. Now, why did I pick this electron pair to share? It's totally arbitrary. It doesn't matter. I could have picked any of these pairs. The only one that I don't want to share is this lone pair on the central oxygen. The reason being because this oxygen is the one that has an electron deficit. If it's already short on electrons, it definitely can't share its lone pair. So I'll redraw my structure with a double bond between these 2 oxygens, and this oxygen still has its 3 lone pairs. So now we can reevaluate the octet rule. We have 2, 4, 6, 8 electrons around this oxygen, 2, 4, 6, 8 around this oxygen, and 2, 4, 6, 8 electrons around this oxygen. So the octet rule is satisfied. All right? So the next step we want to do is evaluate for formal charges. So we do this, or I like to do this, by drawing in all of the electrons that are represented by these double bonds and sectioning off each one of the atoms so that I can see how many electrons are directly around it. So first I have this oxygen. Oxygen comes to the table with 6 electrons. That's how many valence electrons it started with. And I subtract the number of electrons that it has directly around it. So here I have 1, 2, 3, 4, 5, 6 electrons for a total charge of 0. Now I move to this next oxygen, which has 6 electrons when it comes, and now has 1, 2, 3, 4, 5 electrons here. So this oxygen will have a positive 1 charge. So I draw in a positive sign next to it and circle the charge. Next up, I have this oxygen, which again came to the table with 6 electrons, and now has 1, 2, 3, 4, 5, 6, 7 electrons. So it has an overall negative 1 charge. So I write in the negative and I circle it next to my oxygen. So I have a positive charge and a negative charge on the molecule. When I add these two formal charges together, I get an overall net charge of 0. Right? So the net charge is 0, which is good because my original molecule does not have any charges on it. If we had a net charge on the molecule, then we would know that we had added a pair or taken away a pair of electrons somewhere along the line. So the next step that we want to do is to figure out if we have to have these charges on the molecule. Can we minimize the charges by making this negative charge equal out with this positive charge? So the way that we want to try that out is by taking this pair of electrons and putting it into a double bond. Now, you may be wondering, why did I choose this electron pair and not one of these? So, because this is where the negative charge is on the molecule, I know that there's an extra electron on this oxygen, right? That means that if there's an extra electron here and there's not enough electrons here, then if I move some of these electrons into a double bond here, then I should be able to get rid of this positive and negative charge, right? So let's go through and evaluate this new structure that we've drawn, right? So the first thing we always want to evaluate is the octet rule. So we have 2, 4, 6, 8 electrons around this guy, 2, 4, 6, 8 electrons around this guy, and 2, 4, 6, 8, 10 electrons around this guy. So right off the bat, we see that this structure is not acceptable. Because this oxygen has exceeded the octet rule. Right? So, this is not a valid Lewis structure, right? So, even though this molecule has some charges on it, right, it's still the best Lewis structure that we can draw for ozone, okay? So I'm going to redraw our structure down here a little bit cleaner. So we see the final Lewis structure for ozone looks like this. Now, hopefully you guys are cued into the next step here, which is, do we have resonance in this molecule? And hopefully your answer is yes, we do, right? So we have this double bond over here. I could put those electrons back on this oxygen and take this pair of electrons and put it into a double bond. If I do that, what I have is an equivalent structure that has the double bond on the other side, right? Now I have to reevaluate for formal charge, I see that this guy in the center still has a positive 1 charge because it has 1, 2, 3, 4, 5 electrons around it. And this guy over here has now the negative charge. So 1, 2, 3, 4, 5, 6, 7 electrons. There's an extra electron over here, right? So these two structures give the molecule resonance, which is energetically favorable. All right, so let's move on to another example. So here we have the carbonate ion. So the carbonate ion has 1 carbon, 3 oxygens, and an overall -2 charge. So when we're adding up the total valence electrons, we start with carbon. Carbon has 4 valence electrons. We have oxygen with 6 valence electrons, and there are 3 of them. So we have a total of 18 electrons from oxygen. And then this -2 here means that we have to add an extra 2 electrons to our total. So overall here we have 24 valence electrons, total valence electrons. Now if these are a positive charge, that means that we have 1 less electron. So that would mean we'd want to subtract 1 electron, but we'll worry about that in another example. So we have 24 total valence electrons. We're going to put carbon in the center. Carbon with 3 oxygens around it, right? So I've used 2, 4, 6 electrons in bonding. Subtract that from the total, I get 18 electrons left over. So I'm going to go ahead and start putting those electrons around the outside. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So I've used the remainder of my valence electrons, and now I have 0 left over. So the next thing I want to do is evaluate for the octet rule. So I see oxygen here has 2, 4, 6, 8 around it, 2, 4, 6, 8 around it, 2, 4, 6, 8 around it, and carbon has 2, 4, 6. So carbon does not have a satisfied octet. So we're thinking we're going to need to share a pair. So I'm going to share this pair with carbon. Could have been any of the pairs of electrons, it doesn't matter. And I'm going to rewrite the structure. Now we'll reevaluate the octet rule. So we have 2, 4, 6, 8 electrons around this oxygen, 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around this oxygen, and 2, 4, 6, 8 around carbon. So now everybody has their octet satisfied, right? So the next thing we want to evaluate is formal charges. So if we look at, we draw in all of our little electrons here. And again, you don't have to do it this way. This is just, I'm a visual learner, so this is helpful for me so that I can see where the electrons are and who they're closest to. So first I can look at this oxygen, which again, oxygen comes to the table with 6 electrons. And here it has 6 electrons for a total charge of 0. Carbon came to the table with 4 electrons, and it has 4 electrons, 1, 2, 3, 4. electrons directly around it for a total charge of 0. And then we have this oxygen came to the table with 6 electrons and has 7 electrons here for an overall charge of -1. So we'll draw a negative charge over here. We see that this oxygen is the same as this oxygen, so we know there must be a negative charge here as well, right? So next thing we want to do is make sure that our total charges don't add up to anything other than this -2, right? So we have a -1 charge here plus another -1 charge gives us -2, so our charge is correct. So, does this molecule have resonance? Yes, it does. We can easily take this bonding pair and put it back on this oxygen and take one of the other lone pairs on the other oxygen and put it into a double bond, right? So, when we're drawing resonance, try that again. This is the way that we will commonly write them. Now I'm going to go a little bit faster this time because hopefully you guys are catching on to what we're doing here. So I have these 3 equivalent structures for carbonate ion. So I have the double bond on this oxygen, and then this oxygen, right? All of these structures are equivalent, and what they mean is that we have delocalized the double bond. Right? Another consequence of this is that we have the charges migrating around the molecule. So when we have these charges moving around like this, we say that every one of these oxygens has part of these negative charges, right? So that's another way of thinking about this idea of delocalization. We've moved these extra electrons all around the molecule, so every oxygen has a little more than a -1 charge. Next up, let's do the nitrate ion. So nitrate, NO3, with a negative charge. Nitrogen comes to the table with 5 electrons. Oxygen comes to the table with 6 electrons, and there are 3 of them. And we know the negative charge means that we have 1 extra electron. So, again, we have a total of 24 electrons. I put the nitrogen in the center with the oxygens all around, and I subtract the bonding electrons from my total, 2, 4, 6. And we end up with 18 electrons, which again, we can put all around the outside. And now we've used up 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. I want to caution you guys, I always do this counting. It may seem like it's a waste of time, but it's really easy when you start throwing electron pairs around here to accidentally add an extra pair. So I'm just trying to make sure that I haven't added any extra electrons here. So the next thing we want to evaluate is the octet rule. We have 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around this oxygen, and 2, 4, 6 around nitrogen. So nitrogen does not have a satisfied octet, which means that we're going to have to share some electrons. So I've rewritten my structure here. Now I can retally my octet rule. 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around this oxygen, and 2, 4, 6, 8 around this oxygen. 2, 4, 6, 8 around nitrogen. We are good to go. Octet satisfied. So the next thing we want to evaluate is formal charges. So again, come in here and draw in my beautiful electrons. And I see that this oxygen came to the table with 6 electrons. And here it has 1, 2, 3, 4, 5, 6 electrons. So it has a total charge of 0. These has 6 electrons when it comes to the table. It has 1, 2, 3, 4, 5, 6, 7 electrons here for an overall -1 charge. Same here, we started with 6, we ended up with 7, so we have an overall -1 charge here. Nitrogen came to the table with 5 electrons, and here it has 4 electrons, 1, 2, 3, 4. So it has an overall +1 charge, right? So in this case, we have 2 negative charges and 1 positive charge. So we have 1 positive and 2 negative. So our overall charge is -1, which is good because that was the charge on our polyatomic originally. So the next thing we want to evaluate is, can we minimize the charge on this structure? So again, we could take this pair of electrons and put it into a double bond, but I just want you to recognize here, hopefully, that if nitrogen has a satisfied octet and we add some more electrons around it, then immediately we see that we're going to have we're going to be breaking the octet rule with nitrogen here. So there's no other structure that we could draw that would have these charges cancel out. So our final structure will look like this, right? Where we have a positive charge on nitrogen and 2 negative charges here. Hopefully you can also see that this guy has resonance, right? So we could draw 3 other equivalent structures for nitrate. All right, so the next thing we need to talk about is the expanded octet. So if you are an element that's in row or period 3 or below, you can have an expanded octet. The maximum number of electrons for an atom that can have an expanded octet is 12, right? So looking at the periodic table here, carbon, nitrogen, oxygen, and fluorine are all in row 2, which means they cannot have an expanded octet. Phosphorus, sulfur, chlorine, selenium, bromine, and iodine are all able to have an expanded octet, right? So these guys can never have an expanded octet. These guys are able to have an expanded octet. So now let's look at an example of an polyatomic ion that has an expanded octet. So this is the phosphate ion. So we start out, just like always, figuring out how many valence electrons we have. So phosphorus comes to the table with 5 electrons. Oxygen comes to the table with 6 electrons, and there are 4 of them, for a total of 24 electrons. And there are 3 extra electrons on the molecule here. So we have, let's see, 27 is 32 total valence electrons. So I'm going to put phosphorus in the middle and surround it by the 4 oxygens. I've used 2, 4, 6, 8 electrons in bonding. So now I have 24 electrons left over. So I'm going to put those all around the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So now I've used all of the rest of my electrons, so I'm good to go. So first thing I want to evaluate is the octet rule. So here we see that phosphorus has 2, 4, 6, 8 electrons, and each one of our oxygens has 2, 4, 6, 8 electrons. So the octet rule is satisfied. So the next thing we want to do is evaluate the formal charges. So I'm going to draw in my electrons, and I see oxygen came to the table with 6 electrons, and here all of my oxygens have 7 electrons, which means they all have a -1 charge. So I'm going to draw in my -1 charge on all of my oxygens. And looking at phosphorus, phosphorus came to the table with 5 electrons, and here it has 4, which means that there is a positive charge on phosphorus. Now, hopefully you're already thinking, well, if I have a positive charge here and I have 4 negative charges around it, then I can share one of these extra lone pairs with phosphorus, right? So if I share that lone pair with phosphorus, I get, sorry, my drawing is getting a little bit small here. Right, I get this new structure where I have a negative charge on each one of these oxygens, no charge on this guy, and now phosphorus has 5 electrons directly around it, so there's no charge on phosphorus. So we see there's a -3 charge overall, which is good because that's what our polyatomic came with. So now if we evaluate the octet rule, we see 2, 4, 6, 8 for for oxygens, octet, and 2, 4, 6, 8 for this oxygen, 2, 4, 6, 8, 10 for phosphorus. Now, if it was one of these guys in the center, this would be an incorrect structure. But because phosphorus is one of the atoms that's allowed to have an expanded octet, this is an acceptable structure. And we're done.